Today we're going to look at association and correlation and a little bit on regression as well. They're all very much related topics and quite prevalent in research literature, and you'll see the article coming round mentions some of these topics. So just to recap very briefly on what we did last week, we looked at this thing called the multiple comparison problem and considered what would happen if we had multiple groups that we needed to compare. So we had a research article that we looked at where they were considering essentially the weight of different dental materials and looking at their performance based on that measure. And we looked at the weight of Star Wars military personnel, grouped by their rank. And so we set about using some data that we were able to download from the QM Plus site for the course. We set about answering this research question, is the weight of the multiple groups different? That's the multiple groups defined by their rank. And specifically, we used analysis of variance to answer the question, or to answer the null hypothesis that there is no weight difference between any of the groups. And if you remember, analysis of variance just answered that question. It wouldn't tell us which ones were different. It would just answer the question, are any of the groups different? In fact, it specifically answers the question whether the means of those groups are different. And so can anyone remind us what we found? Because I imagine you pondered it for the last 7 days as an important thing to think about and spend time on. Can anyone just remind us what the main findings of our brief study were? Yes. Okay, so we did find a statistically significant difference between at least one group and the others. And if you remember, when we all randomly sampled the data, and some people didn't find a statistically significant difference. And so there was actually a variation amongst the experiments that we all individually undertook. And then we did this thing called Tukey's post hoc test. And can anyone remind us what that showed us? Pardon? Okay, that's right. It pinpointed which of the groups actually showed a statistically significant difference from the others. So there we now have two tools that allow us to assess multiple groups. And so when we find ourselves in with a research question that requires us to find the difference or look for differences between multiple groups, we now know that we can go to tools such as analysis of variance and Tukey's post hoc test. I also mentioned this thing called Bonferroni's correction, which is a way of conservatively adjusting for increased likelihood of seeing an abnormal result. There we go, that's this written down. And now, of course, because this is a hot research topic, then the burning questions are, what does this all mean? Why did we see these differences? Why is there a difference between each of the groups, or at least some of the groups? And so that then leads us to formulate further research questions and undertake further analysis. But before we do that, I want to try and set a little bit of context with the article that was going around. Does everyone have a copy of the article? I need a copy of the article. They should. Can someone wave them around? Where did they get to? There were 50, and I'm sure there's not 50 people in the room. Ah, there they are, over there. So I'll just wait for those to go down. You can download it off the website, which I think I'm going to do. So back on our favourite QM Plus webpage, if you go down to lecture 5, where is it? Oh, here we go. Lecture statistics. You click on the heading. And you should see this, and you scroll down to lecture 5. Firstly, you'll see there's today's slides as a PDF. And here there's this document, Slayton et al., Association and Regression in Dental Research. So you can look at the too much work. Oh, there you go. So this is the article. And so you can flick through that. If you quickly read the abstract, you may glean some information of what this article is about. Essentially, however, they tell us in their introduction, as we learned that we should do, what the purpose of this study is, what their research question is. And they are interested in identifying whether there's genetic markers that are associated with dental caries or dental caries susceptibility. And that seems to be, that's the thing they outline in the introduction. However, later on, you'll actually see some other aspects of their research that they're interested in, the questions that they didn't outline in the introduction. And in fact, if I was to criticize this paper, I would suggest that they haven't outlined all of their research question in the introduction. Is there a spare paper that I can grab now? Excellent. Yeah, brilliant. Thank you very much. So if you don't have one, either share, download it, or come and grab one from the front. So anyway, they use this word here. They want to see if there's an association between two things. Now, when we see that in research literature, that's not just an acquaintance. It's not an informal English term, but it's a well-defined statistical term. So we should be thinking in terms of they must be doing some sort of specific analysis to test for this. This is a quantitative thing that they are doing, or likely to be doing. And we find out a bit more about what they've done in their statistical analysis section under materials and methods. They tell us a bit about how they've organized their data. But they go back and they show us they talk about the association of individual genes with caries susceptibility or resistance was assessed using chi-square analysis. They also do something else. They say the association of caries levels of S mutans with lactobacillus was performed with chi-square test. In addition, they used regression analysis to investigate main effects in the models. And then they have this last statement here. A power analysis demonstrated that a statistically significant correlation of 0.3, so we go get this word correlation, with a single-sided test with alpha equal to 0.05 and a power of 80% can be found with a sample size of 78 or more. Does anyone want to come up and tell everyone what this all means? I can see everyone raring to go. Yeah, me, please. No, apparently not. I didn't think so. However, perhaps bear in mind that, I'm going to use that sacred word again, under exam conditions, if you were to be presented with a paragraph like this that had come from a research article, you might be expected to know what this means. And there's lots of things in there that you might not be really expected to know what they mean, or you might not know what they mean. However, there's lots of things in there that either we have covered or will be covering. So, for example, last week I gave a rather pathetic attempt at explaining statistical power. However, what we did do that hopefully was a little clearer was the practical example that we all get different p-values when we do different experiments. And what this 80% power thing is saying here is saying 80% of the time we'll get p-values that agree. So either reject or accept the null hypothesis. So that's basically what that's saying. So it's like saying 80% of the class will correctly accept the null hypothesis. So 80% of the class will get roughly the same p-value. And they found that you need 78, you need to measure 78 things to be sure of that, or to achieve that level of power. And then they've got this other thing we have briefly mentioned, a single-sided test. So they're doing a directional comparison, looking for whether something's bigger or smaller. And alpha equals to 0.05, that's their chosen significance level. So they're going to compare their p-values to that. So there's lots of information in this small paragraph. And actually, if we don't understand what they've told us here, then there's very little point in us reading the rest of the article, because we won't understand what they've done anyway. We might read their discussion at the end and their conclusions, but we have no idea whether we agree with them, or whether what they've done is sound, or even what the limitations are, if we don't understand, at least to some degree, this paragraph. So, for example, in their results section, they make a few statements. Now, you might be asked to give a critique of such a paragraph in light of what we do or do not know about a chi-square analysis, or what we understand from the other results presented to us. So let's just have a brief look at this. It tells us that chi-square analysis of S mutans levels in children compared with those without dental caries demonstrates a statistically significant positive association with caries. And they give us a p-value. It looks quite small. It's much less than their 0.05. So they're saying that there's a statistically significant association. And you can go on and read this. They refer to some results in table 3. One thing I will point out is they, here in their results section, I consider this to be a point of discussion, not strictly results, because they're now pointing to other literature. This isn't their results. They're pointing me towards something that may not be objective fact. And so I don't like that being there, and I think it should be in their discussion section. Now, perhaps, if you were asked to give a critique, that's something that you might pick up on as well. And so there's this table 3, and we should be expected to know, when we look at that, at least understand the nature of this data that they're showing us. Now, I should point out, I'm not an expert in this area, so this is not my research field, and yet, even without being an expert in the actual field that they're operating, I can skim the paper, have a reasonable idea of what's going on, and critique the results and the analysis, even without being an expert in the exact research field. And that's simply because they've laid out their methodology, they've told me what they've done, and I understand what they're telling me. And these are the kind of skills that as researchers we need to develop, especially as the clinical disciplines are extremely interdisciplinary in terms of research. So we're never going to be the expert across the board. So we need to be able to quickly understand what people have done, but equally we need to be able to describe in a clear way what we're doing so that other non-experts can understand our research and decide for themselves whether they believe what we've done, or believe our results, or agree with our conclusions. So anyway, I've introduced that as a paper that uses or mentions the 3 statistical techniques that we're going to talk about today in today's session. So that was simply, I logged on to the Journal of Dental Research, searched for chi-squared test, and that paper popped up in the list. And that's an exercise you can do yourself, if you so wish. You may not. Anyway, so we're back to this slide again, where we showed that last week, using analysis of variance, we were able to show a statistically, or we found rather, a statistically significant difference between the mean of at least one of our groups compared to all of the other means of all the other groups. And when we undertook Tukey's post-hoc test, this revealed statistically significant differences in the mean weight between multiple groups. For some of us, that will have been all of the groups, and for others, it will have only been some of the groups. But however, there was a statistically significant difference in the mean weight of or the means of the multiple groups. And again, we have this discussion point. What does this mean? Why does it happen? Now, this is where we begin to get into this area where there's more than one way to do things. So we're going to quickly look at another way of reslicing this problem. So using analysis of variance, we simply compared the means of multiple groups and made this assumption that the data in those groups, or the weights within those groups, was normally distributed. Now, there's lots of reasons we might not have been able to do analysis of variance, or may not believe that result. Now, what we can do, we could ask a slightly different question, and rather than asking this question of whether the means of all the groups are the same, we could say, is the weight within each rank, or within each group, distributed in the same way? So that they might not be normally distributed, So you might have the lower ranks might be really heavy and the higher ranks really heavy and the ranks in the middle much lighter. So you would have something that didn't look very normal at all. So if we plotted say rank along that axis, weight up there, we might have for the lower ranks really high weights, like this, lower weights in the middle, and then for some reason really heavy senior ranks. I'm not saying this is what the data looks like. We just have to be aware that that doesn't follow our typical normal curve, which looks something like that, which would say perhaps the ranks in the middle are heavier. Anyway, so we don't know, if we don't know what the distribution's like, or we're interested to know whether the distribution of weight in each rank is the same or not, then we can look at association tests. So I've written here that association tests whether the frequency of occurrences is the same amongst two or more categories. So do you remember we did these frequency tables in one of the very early sessions, and we plotted histograms where we plotted the count or the frequency of occurrences. So we can actually compare these frequencies amongst categories, and we might set up a null hypothesis that looks something along the lines of this. The distribution of category 1 is the same amongst each of category 2. This is very similar to what we're asking with analysis of variance, but it's subtly different because we can compare in the broadest sense the distributions rather than simply comparing the means. So you could have two groups with the same mean but very different distributions. So we could ask this research question: is weight associated with rank? Now, in what we're about to do, one of the things that one of the flexibilities of the test we're about to look at is that it can work with categorical variables. In fact, it works with categorical variables. However, we have weight, which is a continuous variable. It goes on a continuous scale from any number to any number. It's a continuous variable. So the weight of a person can't be less than 0. Can't be 0. But it could be any number up to, say, some maximum ever recorded. But what we can do when we have such a situation, if we want to use a general test that works with categories, is we can categorize the continuous variable. And that's fairly straightforward. We do it all of the time. So on a questionnaire, you may see age, 20 to 30, 30 to 40, 40 to 50. Suddenly, age, the continuous variable, has been categorized into discrete groupings. And so we can do that with weight, and we could naively perhaps categorize into 3 groups: underweight, normal weight, and overweight. And we could choose what those categories are. They don't have to be equal sized, they're just categories. Now, rank is automatically a categorical variable. In the simplest case, it's a nominal variable. So we don't, although it's implicitly ordered, we don't have to treat it as such. We can ignore the ordering when we're looking at a comparison of association. And when we're trying to associate two categories like this, we use the chi-square test. So you'll often see it written as chi-square. sometimes you'll have the D appended on the end. I personally prefer the D. It makes me feel very uncomfortable calling it the chi-square, because it's simply, mathematically, you'd write it as the Greek chi raised to the power 2, which in all other fields would be called squared. So I have no idea why someone, I suspect in some seminal piece of work, there was a typographic error, somebody forgot the D and it stuck. But you may see it being called a chi-square or chi-squared test. They're both the same thing. Personally, I prefer the D. And so the chi-squared test will be compared, we can use that to test this null hypothesis that the distribution of weight level is the same for all ranks. And what you'll see when a chi-squared test is used is the data recorded in what is known as a contingency table. In this case, I don't think it means a backup table, as you would say with a contingency plan being a backup plan. It's just a contingency table is a table of frequency of occurrence. So if we look at this one, we have all of our categories. So we have rank listed here, and weight level. So I've called it weight level because it's now a category. And that category is either underweight, normal weight, or overweight. It's not a continuous scale variable. So we've called it weight level. And then for each rank, say captain, I've counted the number of times that we find a captain who is normal weight. In this case, there's 4. And say, how many sergeants are there who are overweight? 218. If we briefly look at the table 3 from that paper, they have a similar thing. They have categories of caries or no caries. So in the case of looking at S mutans, they have, okay, if we have a patient with caries, what's the level of S mutans detected? And they've probably gone on in that paper to describe exactly how you determine what the level means. But what we know, just looking at this data, is they have categorized the level of S mutans into none, low, medium, high. So in this case, we have 16 individuals testing positive for caries who also have a medium level of S mutans. So a similar thing. So this is a contingency table. Well, there's actually 2 contingency tables here. Just ignore, you can ignore the p-values just for the moment. So we're going to generate this data, or some similar data, and because I know, again, everyone opened up SPSS and has already been onto the website and looked for the data and has probably already done this, so we can all go home early. But if that's not the case, hang around a minute longer and we'll go to the QM Plus website, especially whilst we're waiting for SPSS to go through its rather long load time. And if you are at the QM Plus website for the course, remember you can find it by typing into the search bar DIN 7002, DIN 7002. You search for that, the course comes up, and you get the familiar graphic at the top of the page. And then if you scroll down to statistics data, once again, you'll see last year's data sitting there, and it's not that data that you want. It's hidden, so you have to press on the statistics data title, and that all of the titles to these sections are links. So if you click on the title there, so it says statistics data, it takes you to another page, and if you scroll down this page, you'll see at the very bottom, Lecture 5, 2014, example data for association, correlation, and regression. And when we click on that, fortunately, I pre-opened it all, so it opens up very quickly on my machine. You should download and see something that looks like this. So this is an extension of the file that we looked at last week. Can I have a show of hands if you've managed to get to this point? Got a reasonable portion of people seem to have it. If you don't, again, please work with someone close to you, or not so close, work with someone else. Try to resist the temptation to send yet another email or Facebook message. Unless you're liking the course page, in which case, carry on. So, fortunately, we can generate a contingency table very easily when our data is in this format. So let's just have a look again at what we've got. We've got just an ID number. That's just an arbitrary number for each, but it's unique. It uniquely identifies each individual in this data set. We have their rank listed. We have their weight, which was recorded. We have their type. We're not using that anymore. And now we've got this new variable, their weight to level. So let's suppose that instead of going recording everyone's weights, we actually just recorded whether they were underweight, normal weight, or overweight by some set of predefined criteria that we would have stated in our materials and methods section. So the first thing we're going to do is, as with last week, we're just going to sample the data. So we just decrease the numbers. I think there's 100,000 cases in this file, and we're going to reduce that down because we don't need that many cases. So if we go to the data menu, and if you remember, there is, it says, is it data? There should be, can someone remind me where it is? So, excellent, I'm glad someone listens in this course. I forget. Select cases, excellent. So under select cases, random sample of cases. I'm going to sample that. So we've selected random sample of cases. And we're going to take approximately 10% of the cases, just because we can. And it does mean we're all going to get slightly different results again, but hopefully we'll be in general agreement. So once you've selected approximately 10% of cases, press continue. And then you press OK. And if you go back to your data window, the window menu and the data file, you should see that a whole bunch of them have been crossed out, and then some have been left selected. So if it's got a cross through it, it's not selected, and only 10% of that file have been selected. So now we're going to look at analyze descriptive statistics And we can, instead of doing what we've done previously, where we've looked at some of those descriptives like mean and standard deviation, when we've got these categorical variables like this, we can't calculate a mean or standard deviation. And that's why, essentially, for categorical data like that, the contingency table is our descriptives. It's another way of descriptively presenting the data. And unfortunately, in this case, SPSS has let us down. It doesn't call it a contingency table. It has this thing called crosstabs. So if we click on Analyze Descriptive Statistics Crosstabs, then we can choose which variables we want in the rows and which in the columns of our contingency table. So I'm going to put rank in the rows, and then its weight level I'm going to put in the columns. Remember, we use these arrows in the middle to shift things from one column to the other, from one box to another. Once we've done that, we can press OK. And you should see a box that looks something like that. You might have very slightly different numbers in there. It might look different. See, in mine, I haven't managed to pick up any commanders. Because my sample size is 10%. There aren't many commanders in this data file. And I haven't picked any up. Some people may have. Incidentally, can I see a show of hands? See if anyone's picked up a commander in their experiment? No, none at all. It's a shame. So we might need to, that's kind of indicative that our sample size isn't representing truly our population. Let's not worry about that too much for now. We covered a lot of that last week. So here we've generated our contingency table. And so we can just look and simply, as I said before, we can see how many of each category exist in this sample. So again, sergeants, we've got 97 underweight sergeants. On my screen, how many normal weight captains do I have? Excellent. So then once we've got the data in this format, then we're ready to look at the chi-square test to test whether there is an association between the weight level and the rank. And we can go back to exactly the same menu option, which I'll get to in a moment. So under Analyze Descriptive Statistics Crosstabs, if you click on Crosstabs, everything should be set up as it was before to generate that table. This time, if you click the Statistics button, and you'll see that we can choose chi-square as an option. Fantastic. We don't have to do anything. In the past, I have actually showed people the mechanics of how this all works. And I've since discovered that no one was very interested in that. I think it's really interesting. There's great ways to understand the data. Very few people share my enthusiasm. So on this occasion, you're lucky. We're going to tick a box and use a calculator to do it. So we click chi-square, press continue, and press OK, and we get the same boxes again, except we also get this additional chi-square tests box. As I have said before, one of the really key things with SPSS and this course is actually just learning what parts of these boxes are important to look at. Of course, if you're interested in the mechanics of how this all works and certain subtleties of the analysis, every number there will be of some use. But generally speaking, and especially if you're just trying to report findings to colleagues and peers, you really are only interested in a couple of numbers here. And so, in fact, on this one, I'm only interested in one number. Would anyone like to hazard a guess as to the... Okay, so we've got significance. I can see three numbers under significance. Does anyone want to hazard a guess as to which one? There's only three, so you've got a pretty good chance of being right. Well, I'm going to go for the one that's the top row, listed by Pearson chi-square, because I was undertaking a chi-square test. And what does it mean if we get one that's 0.000? Significant. It's a really small number, and it hasn't bothered listing exactly the number of decimal places. Once you go below 1 in 1,000, from generally speaking, that's going to be enough for us. So much of the research that we undertake, our significance level will be set around 95% or 0.05 level. So a P of 0.000 something is certainly statistically significant. So now I have this result. So originally we had this null hypothesis that there is no association between the weight and the rank category. I've cross-tabulated and run a chi-square test, and I've got a significant result. What does that mean? I reject the null hypothesis, and so can someone give me a statement as to... Yeah, okay, so there is an association between the weight and the rank. Well, there is a statistically significant association between the two. And that's what we found out. That's probably not earth-shattering, and you may be questioning whether we've actually discovered anything different to what we discovered last week using analysis of variance. We still haven't here got information necessarily about the multi-group comparison, but it's important to realize that there are multiple ways of doing the same thing and looking at similar types of analyses. Is this one better than the one we did last week? Define better. It serves a very slightly different purpose. So again, mentioning that horribly ugly word, exam, I see people's heads turn when I say that. That's brilliant. The power of one word, eh? If you were asked to suggest a way of analysing some results or answering a research question, there's not necessarily a right or wrong way to do it, but there will be different ways, and what we would be looking for is whether you had used an appropriate method. And so when you come out, certainly last year there was some anxiety that people inevitably come out and discuss what they've done. How did you answer such and such a question? And someone says, well, I did this because da-da-da-da-da, and they sound very eloquent, and you go, oh no, I did it this way. And they go, oh no, I wouldn't do it that way. Well, you know what, that's actually what happens when we write a paper. We write a paper, we submit it, a reviewer comes back and says, oh, no, I wouldn't do it that way. But then someone else will say, no, that's fine, that's what I would do. And there's multiple ways, and what we're looking for is to try and develop the skills and the way of thinking that says, actually, for this problem, I would choose this method, and this is why I would choose it. Is it right or wrong? well, you know what, different people have different views. Let's not get hung up on that. Have you, is it an appropriate method? Does it answer the question? Have you set, can you answer your stated null hypothesis using this method? If you can, then what you've done is by and large correct. Anyway, while you ponder this fascinating topic and wonder how on earth you'll ever get through January, let's get back to having a look at some of the other aspects of the data analysis that I wanted to discuss today. There we go. That was just a printout, so you've got this in the notes of the contingency, of the chi-squared test results. Now, this is so association is in some ways similar to the analysis of variance, not in every way, but it's telling us again about whether things, multiple groups have the same or different distributions. When we find that there is an association between distributions, if our categories, say rank, are in fact ordered, so at the outset I said we could just ignore the ordering of rank and just treat it as a nominal variable, because if we're not interested in the ordering, then for our purposes it can be considered to be arbitrary and nominal. But if there is actually some underlying ordering, then we can start to look at this thing called correlation. So okay, well there's an association between the there's an association between rank and weight distribution, but is there a correlation? So this describes the strength and direction of relationship between two ordered variables. The key is that these things are ordered. And the strength, I said before that the value of the correlation coefficient, so whenever you measure correlation, it's a value between -1 and 1, or here between 0 and 1, and it's either got a minus sign in front or otherwise. And I did look up, because I think somebody, either here or in another course I teach, was asking for some kind of standard for the different levels of correlation. And so there's a few that have been suggested, and I just grabbed this one, I think off another university website. Again, there's a few, but it gives some idea. So when you're writing or reporting correlations, you may read things like there is a weak correlation or a strong correlation. And at least these words can then be tied approximately to some numbers. So you can see here that the authors that came up with this table or suggested this table suggest if you're going to call something a strong correlation, then we're talking about a correlation coefficient between 0.7 and 0.9. No hard and fast rules, but these are a general guidance. And it helps because although we may or may not like numbers, when we write a research article or report our data, we report it using words as well as numbers. So when we're looking at correlation, so what I mean, and just by correlation, if I've got an ordered variable on here, so something goes up in some order, 1, 2, 3, 4, and I've got something that also changes with some ordering, 1, 2, 3, 4. All I mean is correlation, does it go up as the other variable goes up. So as this one along this axis goes up, that one goes up as well. So small, small, big, big. That's a positive correlation. On the other hand, that's clever. It drew that all by itself. It was exactly right, but I don't know. I have a tablet that reads my mind. This is fantastic. So we can have as one variable goes up, so that variable goes up, then maybe this one goes down. And that's a negative correlation. And there's a couple of ways of measuring this, or a couple of popular standard ways of measuring it. If you have two continuous variables, age and height, for example, or height and weight, then you can use the Pearson product moment correlation coefficient, or just the Pearson correlation coefficient. This is valid when there is a linear relationship, so that's when a straight line describes the relationship between those two continuous variables. There are other assumptions that go into it, but the first things to check are that of linearity, in linear relationships, straight line through the data. So if you have it in Excel and you plot a trend line, a straight trend line, and it looks like it goes through your data points, then it's likely there's a linear relationship. And you have two continuous variables. It should also be what's called monotonic. It's a fancy word for meaning your data doesn't go up and down. So the linear relationship covers that. Just so again, let's say we've got X and Y axis, and we've got some data points plotted on there. Maybe this is two continuous variables, so weight and height. Well, that height in centimeters, weight in kilograms. So we're no longer talking about that weight level that we used earlier. But if it comes back down and wiggles around a lot like that, that would not be considered monotonic. It looks like it does that. Monotonic would mean it just goes up like this. It doesn't have lots of wiggling around going up and down. Now, of course, we've discussed uncertainty previously in the data, and so obviously there'll be some scatter on our data points, represented by my random dots, and they might go up and down a little bit because there's uncertainty there. But if it looks like the actual relationship goes up and down like this, then that's not monotonic. And so when we're looking at correlations, one of the really important things to do is plot the data points, and have a look. Does it look like it's reasonable to calculate a correlation coefficient? So that should always be the first thing we're thinking. We don't just say, I'm going to calculate a correlation coefficient if we haven't visualized the data. We might suggest that that's something we would like to do and it would make sense, but once we've visualized the data, we might discover that a correlation coefficient would be entirely meaningless on this data set, or at least limits our interpretation. So the other correlation coefficient that we can use, that we have at our disposal, is the Spearman Rank correlation coefficient. And this will work with categorical variables, but they have to be ordinal. So they have to be ordered again. They can't be just categories, because having unordered categories, by definition, they don't have no correlation in this in terms of Spearman rank. And it has to have this monotonic relationship. But here we could have our ordered categorical variable, rank, and our continuous variable, weight. And now you can use Spearman rank with two continuous variables. And it has slightly less stringent assumptions on it when compared to the Pearson product moment correlation coefficient. But very typically you will use Spearman rank when at least one of your variables is an ordinal category. So here we might have the weight, let's say, goes up with rank or something like that. And once again, we can do this in SPSS, and we can look at what kind of data output we would expect to see. So, yep. I can try and explain it. Well, I can. It's when the assumption of normality breaks down, but it's one of the assumptions of the Pearson product moment correlation coefficient is that the variation, so this uncertainty in our data, you remember, so I was just talking about you have some scatter, so we've got, let's say, there's my straight line, my linear relationship, and if there's some scatter around that line, because we have uncertainty, we have variance, we have variation, standard deviation. So if I were to look just at this point here, and anything sitting there would have a standard deviation of whatever it is. And sitting here, that would have a standard deviation of whatever it is. The Pearson product moment correlation coefficient relies upon the fact that that standard deviation of your data points, so the uncertainty, doesn't vary along the line. So it means that this standard deviation is equal to that standard deviation, and all along the line. So that's one of the assumptions. Another one is that the Pearson product moment correlation coefficient, again, depends on this linear relationship. Now, because the Spearman rank correlation coefficient doesn't depend on each of these data points having a set interval. So let's say if I'm measuring along here height, that could be 1 centimeter, that could be 2 centimeters. Well, the gap, should we say the interval between those two data points is then 1 centimeter. And so there's a defined interval between each point on my axis, even if it's a continuous variable. Continuous variables like height work because we have defined units for it, so millimeters, centimeters, meters. With the Spearman rank correlation coefficient, let's stick with height, but let's have height level. And maybe we've just got short, call it normal, tall. I don't mean to say that if you're short you're not normal, or if you're tall you're not normal. It just so happens I'm normal, so that's. But what we can't say without any other information, we don't know what the interval is between short and normal. or the interval between normal and tall, because they could be defined arbitrarily. So short could be anyone who is under, I don't know, I don't want to offend, so I have to be careful what numbers I choose. It could be anyone under a meter for argument's sake. But then normal could encompass a huge range. Maybe that we say that normal is anyone from 1 meter to 2 meters. Or maybe anyone from 1 meter to 3 meters. If we're still in Star Wars world, maybe we've got some Wookiees in there and they're normal. If you didn't understand that statement, you must go and read up and watch the movies. And then tall could be anyone over 3 meters, arbitrarily. But we can classify those as we wish. So actually, because the distance between each of these categories is unknown, when I plot them like that, it might look like there's a straight line. And it would be very tempting to go, oh, look, there's a straight line that goes through here. But hang on, it would be just as valid to plot short, then leave a big gap, normal, and then tall. And maybe it'd have something that looked like that. Because the point is, the gap when you've got a categorical ordinal variable along here, that distance on the graph doesn't mean anything. So actually you can't plot a line through it. So we don't have the criteria of linearity anymore. We have this monotonic requirement, meaning that it's not wiggling up and down, but there's still a correlation there. It's just not a linear one, because the linear correlation doesn't actually mean anything in this scenario. So there's a couple of reasons that you might choose a Spearman rank over a Pearson. Because one thing that you do see occasionally, I may have used an example last year, is where someone has coded the categories on their x-axis. So for short, maybe I've got 1. Normal, I've said, is a code of 2. And tall, I've said, is a code of 3. If I'm not careful, they now look like they are scale interval variables, because the gap from 1 to 2 is 1 unit. The gap there, that's just 1 unit. The gap from 2 to 3 is 1 unit. And so then I could calculate a Pearson product moment, but I've implicitly assumed that these categories are evenly spaced out. So you have to understand your underlying data to know whether you can do that or not. There is an example where you can do this. Sometimes when you're looking at exam grades, for example, they will actually be, you might have a category, say A, B, C, but they might represent 90 to 100% being an A, 80 to 90% being a B, 70 to 80% being a C. And so actually they are on a fixed interval. It's just about being really careful that we don't fall into the trap of implicitly assuming there is a fixed interval between categories when actually there is not. And the Spearman rank correlation coefficient allows you to calculate the correlation without making that assumption. And that leads us nicely to another important question. Is there a correlation between the rank and the weight of these Star Wars military personnel? So how can we test this? Do we have, given what has just been said, do I have any suggestions on how we can further our research? Excellent, glad everyone listened. You're going to use a Spearman. So why are you going to use a Spearman? Excellent. So we're going to use a Spearman test. So we're going to use Spearman correlation because rank is categorical and ordinal. And I read that and I think that seems reasonable. So there we go. Rank is categorical, ordinal variable, weight is a scale variable. We could use also no, ignore that. Let's just stick with this. So rank is categorical, ordinal, and weight is a scale variable. So we're going to use a Spearman rank correlation coefficient. So we know that we've decided why we're going to use it. But like I said, there's this other thing, this monotonic relationship that we need to check for. And I've said that the way to do this is by visualizing the data. So let's actually do that. We're going to use SPSS again to help us. So if we go back into SPSS and we go to the graphs menu, that's where we get all of our visualization needs are met. Graphs and then chart builder. And this time, there's many ways that we can plot this data. But because we've got discrete categories, a nice way of doing this is by using a box plot. And I'll just demonstrate to you why that is. So often use scatter plot to just look at all of your data. And so just initially, I'm just going to chuck the scatter plot in there. So you can either watch this or follow. And then on the x-axis, I'm going to put rank. And on the y-axis, I'm going to put weight. And so once you do this, when you visualize what you get something that looks like this. Now, it looks a bit messy, and it's not immediately clear to me what the underlying relationship is in the data set. And so when I've got a categorical variable sitting on the x-axis, sitting across here, I would prefer to use a box plot. Unfortunately, our software just has that functionality sitting there ready for us to use. So I'm going to grab this one that's got a picture of multiple boxes. I'm going to just drag that back up there, and it is maintained rank on the x-axis and weight on the y-axis. If they're not there for you, then just pull them over from this variables box on the left-hand side. And then when you press OK, you should see something that looks like that. Now, I'm not going to go into trying to talk about exactly what every aspect of that box plot means, although I would encourage you to look into it using the LED Statistics website that I've previously mentioned, or any other resource that you find. However, what I do want us all to look at is when we look at these, what we have is a center line here. This center line represents the median value. So it's the middle value in this data. So median is often used when we don't have normally distributed data, so rather than the mean. Sometimes it can be more descriptive. It's low sample numbers. And so we've got the weight, and in each of these categories of rank, or in each of these ranks, we have the median weight, the mid-value weight. So you sort all of the weights in those categories and pick the middle one, and it's drawn a line where that is. And then, depending exactly how a box plot is constructed, which is the thing that's worth going and having a look at. In fact, even look at Wikipedia. There's a reasonable description on Wikipedia. But it tells you there's some variation in those numbers, that uncertainty. There's variation in the weight of each rank. But the thing that we really want to look at is comparing these median values, or just comparing the general, if there's any general trends there. And would anyone like to offer a comment on what we see in this plot, or in your own plot, which may be different? Okay, nobody. So disappointing. Oh well, I'm impatient, so I'm going to crack on. So what I see in this is that there does seem to be a general increase in the median weight with increased seniority or increased rank. So as the rank goes up, there seems to be a small increase in weight. Now, I can't tell from this plot whether this is a statistically significant effect, and I can't tell how strong that correlation is. You remember that table I showed you saying there was a zero correlation, a weak correlation, up to strong, perfect, or was it moderate, strong, perfect correlation. I couldn't tell you just by looking at this, but I can see that there does seem to be some general relationship. I can also see that it looks somewhat monotonic. It might not be, but it's pretty, it's not vastly going up and down. So in my judgment, it doesn't look unreasonable to use the Spearman rank. It appears to roughly show the monotonic, or satisfy the monotonic criteria that's set by using the test. So that means I'm going to crack on and use that. So now I can go to run the Spearman rank correlation coefficient test. I can go to the Analyze menu. Remember, the Analyze menu is where all of this functionality is found. And helpfully, there is a submenu which is listed as Correlate. So that helps give me a clue that that's where I might want to go. And when that submenu opens up, we are presented with three options. We're interested in only two variables, so we go for bivariate. Bi meaning two, variate variable, two variables. So analyze, correlate, bivariate, and we get this box come up. So I'm interested in the correlation between rank and weight in kilograms. So in your variables box, you should now have rank and weight in kilograms. Then below that, you'll see there's this correlation coefficients box. And by default, Pearson is ticked. We're going to uncheck Pearson, and we're going to check Spearman, because we said we're going to use Spearman's rank correlation coefficient. So incidentally, SPSS will allow us to use that ordinal variable for the Pearson calculation. It's not going to tell us not to do it, so we need to know which one we actually want to use. I'm going to leave it as a two-tailed test, and then we're going to press OK. And you get another box come up, and when we look at this, we can see that we have the rank compared to the rank has a correlation coefficient of 1. That should be no surprise to us. Comparing something to itself should have perfect correlation. Rank compared to weight has a correlation coefficient of 0.073. However, the significance of this is 0.000. Would anyone like to make a statement of these results? Okay, you might not like to make a statement of these results. Is anyone going to offer a statement of these results? Could anyone be convinced ever? There is a significant correlation between the rank and the weight. Anything else? There is a weak correlation. So based on that table, we can call this either a weak or very weak, I guess you could add to it. It's less than 0.1. It's weak correlation. So there's a statistically significant but weak correlation between rank and weight. So this means that although we can show statistically that weight seems to increase with rank, it's very weak, so it may be an inconsequential relationship. And that's something we would decide, perhaps in our discussion, using our judgment as the researchers, as to whether that correlation was really that important. And this is similar to this discussion we've had previously when comparing two variables of effect size. So remember we talked about a minimal important difference being the difference between two things that we'd measure, and the minimally important difference is the smallest difference that we would observe and say that it was really important. And we have a similar judgment that we make with the correlation coefficient. So if it's a really weak correlation, is it actually important? There we go, those are those results there. So let's just write that down. So there, there is a statistically significant, remember in brackets, P is much less than 0.05. We could call it a very weak if we like. But correlation. And what we'd say here, in the correlation, we'd express that as a rho is equal to 0.08, I think is roughly right. Between rank and weight. So essentially, by running this correlation, we have done a form of multiple comparison test. But we're saying there's actually some kind of ordered relationship. It's not just that there's differences between the groups. We're saying there's ordering in the differences between the groups. And that's what the correlation picks up. So if it was just, if the difference between the groups wasn't ordered, then we might find no correlation. Well, we found very weak correlation, but it's statistically significant. You asked me to repeat things as if I have a script that I stick to. What did I say? It's gone clean out of my head. Can someone remind me what I said? Is anyone listening? I try not to listen to myself. You're meant to. Okay, yes. Okay, so the point I was trying to make was that if there wasn't an ordered weight difference between the categories, so let's say the lowest rank maybe had a high weight, then the next rank up had a low weight, and then the next rank up had a high weight, and there didn't seem to be any reason for it that we've detected. It just seemed to go up and down between the different ranks. Then we would most likely find a zero correlation. And we'd probably find that it wasn't a statistically significant correlation. However, what we've found, although we've found a weak correlation or virtually no correlation, we've also shown that it's statistically significant, which is indicative of there not being much variation. So what we're picking up here is more likely to be real than just some random changes in the weight between the groups. But this is very much discussion topic. This is where you can go around in circles trying to convince yourself one way or the other, putting forward the merits of different ways of looking at the results. So we can, if we just think about this a little bit more, we say if this is weight, rank, and then for the lower rank, like I said, it might have a high weight, and maybe even the next rank along also has a high weight. But then the middle ranks, maybe it's a bit lower, and then maybe at the very senior one it's higher. And we might find that the correlation coefficient came out as 0 and had a low p-value, because it's very difficult to tell. We'd also probably see that when we plotted this, using our box plots and the median values, that it doesn't, especially if we look at the spread of that, this suddenly doesn't look very monotonic. Because it looks like it goes up and down. And so that would be saying, well, there's not a correlation that we can detect. So is the question, how do we find out what the coefficient is? Or yes, so we ran the Spearman Rank correlation test, and the correlation coefficient, see, it's listed. So it's listed here on this row, and so if we follow that over, the correlation coefficient between rank and weight, so rank's there, weight's there, the correlation coefficient I've just drawn through is there. Correlation coefficient is that one there, 0.073. It's a very small correlation coefficient. Okay, so that's the correlation coefficient. So that's the level of correlation. The statistical significance tells us whether this is significantly different from 0. So the null hypothesis in this case is that there is no correlation between rank and weight. So if there is a correlation, then we would have to reject the null hypothesis based on our p-value, And the p-value is the number below it, sig two-tailed, and here it's 0.000. Well, it would either have a... Well, you can visualize it. So the first thing always is visualize the data, but the correlation coefficient will have a sign in front of it. So in this case, it's not got a sign, so it's a positive correlation. But you could, if it had a minus sign in front of it, then it would be a negative correlation, minus 0.073.
I want to draw for the first time how you do. I want to draw. Yeah.
Oh.
If you look, for example, children in private school, for example, this group, and then the other group, for example, semi is private, and the third group in a very state school, for example, state. Okay. The first semi, the second one, and the first one is private. You should be driven by physical framework that there is a relationship. The more the bright people, the more likely first. Before you go into class, you have to have a background for your first question. And then you would go whatever the data you're getting from your survey, for example, for the carry, which is the increment of, for example, DSM. So you would get here, for example, the carry level, for example, 1, 2, 3, 4, 5, and so on. And you have private school, and then you have the semi, and then you have this, for example, state school. You will find that the level of theory is increasing with the level of deprivation of the children in certain school. For example, children in private school less likely to have, for example, high level of caring. If you go to semi-private, their care is increasing, and if they are very deprived or state school, their care is high. But you can't draw this line; it's wrong. Because if I put in here a point and I want to look into this relationship, I can't, because it's meaningless. If you compare, if we look at just to look into the continuous variable.
You want a new page?
Yeah. So if you look, for example, to another example, if we have here, for example, DMF, okay, which is, for example, 1, 2, 3, 4, 5. And here you have the age of the children in continuous variable. For example, they are, for example, 5, 6, 7, 8, 9. And then you will find, for example, increasing in the age is stated as increasing in the, for example, DMF. Then you will find a interval scale or scaling. Okay? So did you get what Dr. Pearson is trying to tell you? So if you have, for example, now a graph like this, and you have three categories like ranking, for example, and here you have, for example, a continuous variable. Are you going, for example, to draw a line? Who's going to justify for me? No, we cannot draw. Why? You try to draw a line. Yeah, it makes sense. You want to match the x and y axis. So this is the point of it. So don't be distracted to this small mistake that is very dangerous if you write it in your report. Okay?
Thank you, Saba. This point is important because you will see it a lot, and you will see it in published literature, and it's wrong. And last year I examined a PhD thesis, and I gave a guy passed. He did a really nice PhD, but he had done this, and I gave him a really hard time over it. I was just mean, but it is an important thing. We need to be aware of not doing this. So we found this weak correlation between the rank and the weight, but perhaps that's not satisfying understanding of what's going on in the world around us. And so we perhaps want to expand on our question a bit more and set up some further research. And so we might propose that actually the variations in weight that we see in our military personnel, perhaps they are just down to age rather. They're simply down to age. So we can ask ourselves the question, does weight correlate with age? And under this question, we can then have a null hypothesis that there is no correlation between age and weight. That would imply that any weight variations are random amongst or independent of age. So age would not be a factor. That's what we're saying in that null hypothesis. There's no correlation between age and weight. Age is not a factor in weight variation. And in this case, we can look at our variables and we see that age is a continuous variable and so is weight. And consequently, we can use Pearson product moment correlation coefficient, which I will always refer to as the Pearson correlation coefficient because it's far too long otherwise. And so if you were to write it, I certainly wouldn't penalise anyone for not writing out Pearson product moment. I think, although there are different versions it's generally accepted that you mean the Pearson product moment correlation coefficient if you say Pearson correlation. So we can go back into our software and look at this, because you may have noticed earlier that we had age in our data set. So we so if we go back to the data set window, you'll see this column here, age. So for every trooper, we also know their age. And the first thing that perhaps we want to do is visualize the data. So that's a really important thing to do. So we're going to go and we're going to look at graphs. We're going to go to the chart builder. And this time, because we have continuous variables on both axes, we are going to look at a scatter plot. So when questioned as to what the appropriate way to visualize the relationship between two continuous variables, you may well excitedly say a scatter plot would be a good way to do this. It's not the only way to do it, but it's a pretty good way because well, you'll see, hopefully. So in here I've currently got rank, but I don't want rank now. I'm comparing age. So there we go. We have age on the x-axis and weight on the y-axis. And once you've done that, you can press OK. And you'll see something looking like that. Is this linear? So yes or no question. Louder. Excellent. Thank you. Thank you. So it appears that there's a linear relationship. And if we think our eyes might be a little bit wonky and we want to just double check this, we can double click on, no, that didn't work. We should be able to double click on the plot and it should come up with another window like this. And you'll see there's this menu bar here that I've got. Hopefully you've got the same one. And that box there says add fit line at total. So it's just saying, can I fit a straight line to the total data set, or can I fit a line, actually not even a straight one. And when you click on it, you get this box, and you'll see that linear is already selected. And if it's not on your computer, you want to select linear. And then just close that. And as if by magic, and you can close this box as well, a straight line has now appeared through the data set. So even if we've got a fancy curved display, we know that that's a straight line. And it does very much look like there is a linear relationship between age and weight. It looks like it's, visually, it looks like it's a linear positive correlation. As age goes up, so does weight. And there's some spread because this won't always be true. And we can test this statistically, going to analyze, correlate, bivariate. Let's analyze, correlate, bivariate. You need to take rank out of the box. So you see this little, select rank, if you've got it in there, select the little arrow that's facing left to take it out. Then select the age variable. And click on the arrow that points right. And this time we're not doing the Spearman because we seem to have satisfied the criteria for running a Pearson correlation, so we're going to look at Pearson. And then when we press OK, we get another wonderful box come up, and it's very similar to the previous one. We can compare the Pearson correlation coefficient, which is this top line. So this number here is the Pearson correlation coefficient, or R. And so we can see here that R is equal to 0.94, roughly. So if we look up on our table, that's a strong correlation. So there's a strong correlation between, a strong positive correlation, I should say, between age and weight. And is this a statistically significant correlation? Yes. So we can see, what do we have? So we see that. So we can write something along the lines of, there is a statistically significant, p much less than 0.05. I'm going to say positive, or let's call it a positive strong correlation between age and weight, and that's what our results show. And I'm aware that we've been going for a good chunk of time now, so we're going to take a 10-minute break before we come into land with some exciting regression. But before you can leave for a much-needed break, Saba would like to say a few words.
So when you see, when we go into, for example, a graph, like the one now, for example, talking about this in the leader, small I. If we give you a graph like this, and we ask you to look at this graph and describe it. Here are how we describe it. So you have to be careful for every single word. When we, for example, there is a strong relationship, you have to put between brackets with the position. For based as there is a strong correlation. Particularly, we're going to do this result, for example, this graph with the table as well. What is that for our position? If we're going to say a strong, for example, linear or positive, we call it positive relationship, you have to demonstrate that increase in one unit in age, there is increase in that weight. So that will demonstrate that you understand what sort of the relationship you have. And this as well, you're going to apply it in your research when you start doing your work. Okay? Thank you.
Yeah, that's an important point, actually, that so when we look at the graph and we're just reporting subjectively what we see, we can't say that there's a strong correlation because we haven't actually tested that. So these words, strong correlation, have somewhat defined meanings. So we can only state those things once we actually have the numbers to back it up. You can, when reporting the graph, say that it visually appears to have a linear relationship, or that would be fine, but you can't state that it has a strong correlation because you haven't tested it until you've got that table with the numbers to back up that statement.